Good day, ladies and gentlemen. Welcome to our to CGS SOS March presentation. My name is Ali Nasiri Mohaddam. I'm the current chair of the CGS SOS. As you know, we sent announcements for recruiting new members. The term for the existing committee members will end this May, and we are looking for 6 to 7 new members. So please volunteer. This is a 2-year term in which you will commit about 2 hours per month of your time, plus joining the meetings when it goes in person, which we expect it to happen sometime next fall. The deadline for the application is April 2nd, which is a week from tomorrow. We look forward to see you as volunteers to help out and expand the works that we have done so far and build on top of it. Without any further ado, I'll pass this to my colleague, Mr. Sen Hu, who will moderate the session for today. Thank you very much.
Good afternoon. My name is Sen Hu. I'm the coordinator for this webinar, and welcome everyone to join this interesting the topic to discussing about different problems in shoring and the piling cases and the explanation, which will be presented by Dr. Ahmed Mufty today. So first, we'd like to thank for all the sponsors for this webinar, including the CATA's Rock Science, Solar Tank, EBS, Insiger, and the Grounded Engineering, who support this webinar. Thank you very much. And there's the as we know, the coming major conference for the CGS will be held on September 26 to 29 this year in Niagara Falls. So I do believe some of you have submitted your abstract of your paper and it has been reviewed by the committee. So I believe that some of you are preparing to submit your paper by the due date. So and also you are also encouraged to participate this event, and hope this event can be physically for us to get together. So anyway, the details will be announced later in the website and also the newsletter of the CGS. And the next, just encourage and remind for the renewal of our CGS membership if you have not done yet. And we know the benefit may include online access to the monthly Canadian CGS, Canadian Geotechnic Journal, including all the past issue and the special prices for the printed version, as we always use. And the second, you can also print out and the online copies of some quarterly Canadian Geotechnic, the CGS magazine. And also you can find all the past copy of the Geotechnic News magazine, which has been stopped the publication since last year. Then you can also receive the monthly CGS newsletter. And then we can also have provide online access to past CGS conference proceedings and many features and special lectures, and also include the parts of the webinars. Then we may also, once we back to the regular physical meeting, then you can also get some special rate for the member price to attend either the conference or the dinner lectures as usual. Then you can also have an opportunity to participate in the committee of the CGS at a different locality. So please, if you have any question, please send us an email as shown on the screen. Then also have a welcome to visit our website more often. Thank you. The next, yes, and for the webinar, we are going to have a next webinar on April 22nd at the same time. The topic will be the physics and the mechanic property of the soils in the GTA area, which will be presented by Mr. Dimitri Oshanki and Mr. Jeffrey Creer, who are working in the TTC at this moment. And I believe most of the geotech engineer know these two persons, and so they are going to give us a very interesting introduction about the TTC's soil classification, and also give us the case and some comparison for some advanced test result. I believe this will be very interesting topic for in April. So the details will be sent out by our newsletter, and you are also can encouraged to participate. Okay, now it's my honor and my pleasure to make an introduction for the speaker, Mr. Ahmed Mufty today. And currently he is working as a geomechanics specialist in rock test, who is a firm we use a software pretty often. And he got his completed his academic study in the university, the Baghdad, and have his bachelor degree in 1985. Then get his master's degree in 1990 and complete a PhD study in 1997. And after he graduated from the school, he's continued to play the role as the faculty member in the Department of the Civil Engineering in the University of the Baghdad for the period between 1995 and 2004. Then after in 2004, he has opportunity to move to UAE to work in the pilot design and the construction until 2019, when the time is a pretty economic boom in the UAE area for many site development. And in 2019, he joined the rock test in Toronto up to now to join their development of the geotechnics software team for many related to several topics of the geomechanics. And Dr. Mufty has 35 years of including the practical and the theoretics experience in both civil and geotechnical engineering, including slope stability, site investigation, laboratory testing, foundation design, construction of the road embankment, the earth dam, the shoring for excavation, and also the deep foundation. He has a very wide and remarkable experience in engineering characteristics of the soft clays and also gypsum soils. And during the year 2004 and 2019, he worked as the technical manager of the HSSG and APCC, which are two of the largest foundation company in UAE. So during his working, he designed a lot of the shoring work for the deep excavation and as well as the deep foundation work, and more than 100 projects. And his working area including the Mid East, the Asia, and of course including the Canada. So he also have presented the lecture at several courses, including the soil mechanics, numerical analysis, and the geotechnical engineering, from the undergraduate to the postgraduate students. So I'm sure, and he also had more publication, or many publications, including one book regarding the numerical method, and in many conference and seminar. So let's welcome Dr. Ahmed Mufty to give us his presentation today, and enjoying the time. And you are encouraged to send the question during the presentation through the question on the screen. Then we will collect the question, and by the end of after his presentation, we will have about 10 to 15 minutes for the question and the answer. So now let's welcome Dr. Mufty. So that's your turn now. Thank you.
Good afternoon, everybody. Thank you for attending this webinar. I'm Ahmed Mufty. I hold a PhD, and I'm a professional engineer of Ontario. I work in Rock Science Incorporated as a geomechanics specialist. And I need to start my presentation with submitting my thanks to the CGS SOS committee, and a special thanks are to Dr. Ali Nasri Mugaddam and to Mr. Sanhu, and of course to my friend Ali Abdulaziz, who all facilitated and made this presentation happen. And thanks to all the attendees also. The presentation, I preferred not to go into the theoretical issues, or having calculations, or discussing theoretical problems. I tried to make something which would be interesting and fun for the audience in the same time, and it will give some, let's say, I would share some of the experience with you guys, and that's why I chose this topic. The topic is different problems in shoring and piling. I'll show pictures of cases, and I will explain the problem of each case. So the idea is, what if anything went wrong during the work? We need to be sure that our design, our methods, our monitoring systems, everything works fine. Shoring is a very dangerous field of geotechnical engineering for deep excavations. And also the foundation piles are an important part of the structure, which transfer the loads of the structure into deeper, stronger layers of the ground. So let us see some of commonly expected mistakes and some interesting issues that may face a geotechnical engineer during working in shoring and piling field. Of course, these are very limited number of cases I will present. There are hundreds of problems that you may face, but I found this as interesting to show. So I will start with a failure case that happened in shoring in one of the sites in UAE. So this is a water body called the marina, and the site was adjacent to it. The only thing separates the site from the marina was around 10 meters of quay wall and some fill, and there was a part of a concrete conduit behind this part. The design stopped the anchors at this part because the anchors were hitting the concrete wall behind the shoring, but unfortunately the design did not take into consideration the effect of water pressure that still exists behind the shoring wall. The shoring was diaphragm wall, and look what happened after a while after reaching the excavation level. So the wall collapsed and the whole site was filled with water. You can see even the machines were completely drawn into the water, covered with water. Fortunately, the case did not happen immediately. It took some time, like enough for the people inside the site to go out, to run away. But of course, the machines and everything remained in the site. Of course, the problem was solved later with a huge amount of cost and reconstructing the wall and making a full strutting system to support the wall. And the tower is built and everybody's happy now. This is another site that is supported. The excavation the retained soil around the excavation was supported by contiguous piles. Contiguous piles are piles with gaps between them, and these gaps may vary from 50 millimeters to 150 millimeters, depending on the strength of the soil or the rocks behind the shoring wall. The site, when was under design and construction, there was a time schedule to start building the structure on a specific time. We reached the ground level, but nearby, around 50 meters away, there were artificial lakes being excavated and constructed. They were liners, of course, but they were not filled with water, and supposedly the water would be filled after the building is constructed. But what happened is because of 2008 recession, the work stopped, but the lakes were filled with water. So what happened? We got water flowing between the piles from all around the site, and we could not stop it. See how the water is flowing between the piles? And this is another site in the same area. The flow was really heavy, and the only way to work with this situation is to make French drains, and these to be collected by the dewatering system. If the original dewatering system is not enough, additional dewatering system should be installed. In fact, the dewatering was working very fine before the lake was filled with water and the site was completely dry. You have seen how the water was flowing. This is another site in Qatar, Doha, where the shoring was second piles with one layer in some places and two layers of anchors in other parts. But the dewatering system was designed in a good way, and everything was fine. But the discharge levels that we had should be allowed by the authority to some discharge points. But unfortunately, when we reached the maximum level of excavation, there was a disruption in the discharge points released by the authority and delay of approvals, which made the dewatering system unable to discharge the water away from the site. This is in the middle of the city, so we cannot discharge to the sea, and we need to discharge to specific drainage waters, drainage points. Water always is a problem in shoring. Wherever you find water near the shoring, you may have a problem. This is another site with I-beam soldier piles, shoring, one row of anchors, and the dewatering system is working. The site, you can see the dewatering system is well point system around the plot from inside. What happened is the dewatering caused increase in effective stresses around the site, because when you remove the water, the weight of the soil will turn into effective stresses, and that will cause additional settlements that was not accounted for. So the roads around the site were all cracked and settled. You can imagine this if you have a building or existing structures or even services in this area, and you have original water table, then you start dewatering inside. When you dewater, the water level outside will have a drawdown, and the new phreatic line will be lower than the original water table. At this area, at this zone, the effective stresses will increase and additional settlements may happen. these settlements, if occurs, it will it will cause cracks in the buildings and settlement of foundation, and differential settlements also in foundations. So we need to be very careful when designing the dewatering. It's not only dewatering. The dewatering engineer or the geotechnical engineer should calculate how much settlements he's expecting outside. This is another site in Toronto. The dewatering system is installed, but because of some problems regarding the financials of the project, the dewatering stopped. Nobody's paying or something like that, and the rain caused huge flow of water into the site. The site was not shored in this side, shored only in this side, and the retaining wall was only in the other two lines. And see what happened. The whole site with full materials there was flooded. The concrete columns are already sinking in water. Another site from Abu Dhabi, there was a retaining wall here, embedded retaining wall, second piles, and there were supposed to be anchors, tiebacks to support the wall. This part of the wall was in front of the wall. There was a ramp, so the contractor did not stress the anchors properly because of the ramp. And when the ramp was removed, the anchors were loose and forgotten. The wall collapsed immediately after the ramp removed. Anchors are very important, and they are crucial part of the supporting systems for the excavation surroundings. You need to be careful that you leave enough length of the anchor outside the shoring wall so that you can go back and check your stresses, and you stress these anchors back. And the whaler beams should be always clean, because if they are filled with or dumped with material, concrete pieces, and soil, that may bend the whaler beams and affect the anchor's adequacy for continuing to support the system. You can see how much material is collected or above the whaler beam, and see how the anchor strands are damaged. If you want to go back and stress these anchors again, or you want to test them after a while, like 6 months or 1 year, depends how long the excavation will remain open. So you cannot do that because there's no enough suitable length of the strands outside the anchor plate so that you can apply the stresses again. This keeps the shoring in danger. You need always to observe and to be careful of everything happening around the shoring. Never leave a shoring without monitoring. You can go to YouTube and find hundreds of videos of different kinds of failures that happened in shoring. the anchor strands, if it is a stranded anchor, may fail also by overstressing. So if you don't control your jacking and stress the anchors properly, you may cut the anchors, and there will be a problem in these strands. They cannot transfer load anymore into the ground from the shoring wall. So the geotechnical engineer is responsible also to check his anchor's structural capacity and not only geotechnical capacity. And he should follow standard methods of stressing these anchors and testing them before approving the anchor and leaving it peacefully. Also, the anchors should be retested after a while because there will be stress relaxation. Let's go to pile testing. So I will go through a couple of problems, not the theoretical part, but some practical things. See here, for example, the contractor used a leaking jack, and also the two jacks are not identical. So what will happen here? One jack will give a higher load than the other one, and this will cause a differential load on the pile cap, causing different readings in the dial gauges around the pile. Leakage is not allowed in jacks, and you need to stop this test and to replace or repair your jack. Another problem is common, in fact, in pile testing. Most contractors, they do not provide enough length for the reference beams. The reference beams are supposed to be away in their reaction points from the pile being tested, so that there will be no interaction between the pile cap or the pile and between the zone that these reference beams are supported at. So when your reference beam is short, you will get no readings. It's like your pile is perfect, and the contractor is happy, consultant is happy, and the client is happy. But in fact, the reference beam and the pile cap are moving together, up and down. So the dial gauges, which are supposed to measure the difference between a stable, unmoved, undisplaced reference beam and the pile cap, will record no difference in settlement. So you need really to have long reference beams, and sometimes you need to make reference frames. You connect the reference beams, and you need to put one side of the reference beams fixed to the ground and the other side free to count for temperature changes also. I believe you have all heard of web buckling or web crippling. If you support your cartilage system in the test, in the pile load test, on I-beams at the sides, these I-beams should be checked for web crippling and web buckling, and they may be supported by cross strips, welded cross strips at the ends, and maybe stiffeners within their lengths. So this case shows how how web crippling or web buckling is happening. This is very dangerous, considering the safety of people conducting the test and recording the displacements and loads. Another problem in the tests when you construct your pile cap, you excavate, you make your form, and start pouring the concrete. And you're happy. You come the next day, you start testing, and you find huge settlements compared to the loads you're applying, and sometimes tilting in the pile cap. This may happen because you have constructed your pile cap pouring the concrete facing water. Groundwater is here. So you need to be sure there's no groundwater or free water beneath the pile cap while pouring the concrete. This type of pile caps, they should be constructed on gravel layer, and the gravel layer should have a corner pit for a sump pit that you can pump the water out during pouring the concrete until the concrete is fully hardened. Then you can excavate and remove the gravel and check the bottom of the pile cap yourself before you start the testing. This is how this pile cap was at its bottom, and the recorded results of that pile were indicating failure of the pile, and the pile cap was also tilted. We just removed the pile cap and repeated the test, and everything was fine. Let's talk some safety. Piles are usually drilled into a case. First, you install a casing, then you start drilling and inserting the pile reinforcement cage. If the surrounding soil around the casing is unstable and the casing length is not enough, is not following standards, what you will have is a disaster. Sometimes the soil around the casing will collapse into the hole beneath the casing. And see how this worker, fell inside with the soil, and they barely could save him. Fortunately, he was taken out safely. Another problem you may face regarding safety is open excavation trenches that you don't really support because it's temporary. You say it's temporary, but it is very dangerous. In this trench, this side fell later, and one of the workers was buried up to his neck. Fortunately, he was saved without injuries. You need to check your trench stability and whether you need to have a slope enough to make the sides of the trench safe. You need to check trench stability even when you are drilling, for example, diaphragm walls. You have huge machines on the sides working, excavating for the diaphragm wall, and you did not check how much you need a guide wall depth to be sure that there will be no collapse of the soil that the machine is working on and its platform into the trench itself. Pile installation also have problems. If you don't guide your piles with a guide wall, you may face problems. So you need to build a guide wall like this one, reinforced with a light reinforcement before you start drilling or inserting casings. If you insert casings just by coordinates without a guide wall, you will get something like this. This is the end you reach. This is the result of a shoring wall that has been constructed without a guide wall, or even a temporary guide wall, like a steel guide wall, just to guide the casings in the beginning. Then after that, you remove the guide wall. Again, the machine will have a problem in staying in a straight vertical line. Nowadays, the machines are having a tilting control, so you can feel what's going on, but still you can't easily change your direction, especially if the soil is a strong rock or hard material. Sometimes if you don't follow the right sequence of installation of pile walls, you may face fall of the concrete from one side to another, or the soils also may fall into your hole if the casing is not deep enough, and if it is pulled up very rapidly. For example, if you have a cavity and you pull up the casing, then the concrete will fall into the sides during the casing withdrawal and may cause necking in the pile that keeps the reinforcement without concrete. Slurry is important if you have some such cases, but the best thing is to have enough length of casing and withdrawing the casing after the concrete is semi-hardened. So casing removal may lead to voids and integrity problems. You need reinforcement for at least 3 meters below the casing. So if you have a casing and a pile, don't leave the casing in a depth that the reinforcement is not extending beyond it. You need the reinforcement to be extended below the casing, because that reinforcement can hold the concrete of getting pulled up. Working near a dewatering well may cause migration of cement. We will see that in a while. If you have a dewatering well and you are installing a pile nearby, you will wash out the cement from that pile. If concreting starts before the groundwater and the water in the boring stabilize. So if you don't have slurry and you are concreting underwater, you need to wait until the water in the drilled hole stabilizes. Because if it's not stable, the concreting will be not adequate, and fines may be washed out, like cement or sand. Fall of material from sides of the hole inside the borehole during casting. So you need to be sure that you don't have collapsing material around the hole. This we encourage every project to have prior to the project start, to have a trial boring to check how much collapse and to check how much diameter changes may happen through the length of the drilled hole. One of the important causes also of contamination and formation of voids and loss of integrity is raising the tremie pipe rapidly. So you need to keep your tremie pipe at least 2 to 3 meters below the top of the concrete. You push concrete through the tremie pipe into the pile. The concrete will start going up. The tremie pipe should be withdrawn to keep the concrete above the tip of the tremie pipe at least 2 to 3 meters. In foundation piles, time is needed to ensure concrete set before a nearby boring is performed, so that water will not flow from a new pile zone to the next boring, and to ensure no gradient will take place due to fresh concrete pressure. That means you need to keep enough distance between a new pile being installed and an old pile, if the old pile is not hardened yet. So if you have a piling sequence in the same day, you need to choose your pile locations away from each other while sequencing your construction or your installation. Ensuring piles, if the intermediate piles are cast before concrete in adjacent piles is not hardened enough, you will face problems. Like you will have some concrete falling from one to another. So you need to have a good sequence of piling while doing the shoring wall, so that when you do a new pile, it's away from the other pile, at least 5 piles. Like I have shown here, just a fast look. So the sequence is 1, 2, 3, 4, 5. You will not cast this pile while casting this one. So you cast this one, you cast this one, then you go back into the middle, then you go back into the intermediate piles. What if segregation takes place? Segregation happens usually because of unsteady or steady flow or unsteady flow of the water, groundwater nearby the piles. So if there is a flow of water, during concreting, that flow of water may wash the cement and cause segregation. And also sometimes because of low slump, that causes honeycombs, voids in the water, and that in the concrete, and that will act as capillary conduits within the pile. So we see after the pile is finished, we see the pile is bleeding water at its top. It's not from the surroundings, it's from the middle of the pile. You have a look to this one. Sorry. You have a look to this one, to this one. These are from different sides, by the way. But it's a common problem that contractors face because they can't stop the dewatering and they need to cast the piles. So what I usually advise the contractors is to switch off the dewatering well that is nearby the pile. See, this is a dewatering well here. You need to switch off that dewatering well that is around 6 meters away from the pile, within 6 meters from the pile, so that the water flow happening into the dewatering well will not cause a problem of segregation in the nearby pile that is being cast. Also, another issue is very interesting. Sometimes high temperature cycles may cause cracks between the heavy reinforcement and the concrete and allows capillarity. This is very less studied, in fact, this phenomenon, but I have seen it. You may see cracks around the steel bars, like you have 40 millimeters bars, and the pile is heavily reinforced, and there is a huge difference in temperature between the casting and the usage of the pile, and also daily changes or seasonal changes in temperature. So because of the difference in the thermal coefficient of expansion of the concrete and the steel, you may have this problem. See what did happen here? I don't know. What do you think? Usually piles get damaged reinforcement at the top near its cutoff level, not near their cutoff levels, because of no enough wiring, binders for the reinforcement, and basically, and more important, is the inner rings. The cage of the reinforcement is not only a spiral or helical links around, or circular links around outside the reinforcement. You need to install inner rings also to keep the reinforcement in place, and especially at the top part near the cutoff level. If you don't have the inner ring, during the installation of the steel cage and pouring the concrete, you may damage your reinforcement cage. When you do not follow the standard number of and distribution of spacers, every pile steel cage should have spacers to keep it in place. And that's why if you don't have enough spacers, or the spacers are weak and get damaged, you will see the result is having less cover than the design. When you expose the pile head, you will see the cover is less than the design cover. Usually it's 3 inches. See here we have like 4 centimeters, like 1 inch or 1.5 inch. Sometimes also using smaller buckets, because you don't want to bring exact diameter of the bucket, so that you will not pour additional concrete and you lose some concrete. You must use the exact dimensions of the buckets in excavating the borehole of the pile. Of course, if you have a smaller cover than the design, you will get a lot of cost in repairs and delay damages for these piles. You may need sometimes grouting. You may need sometimes to excavate around the pile, expose some part of the pile that is very important for the structural loading, and you will add cover to it. Let's see a design problem. What if the foundation pile is designed shorter than required? In this building, the shoring piles at the edges were very close to the foundation piles at the edges were very close to the shoring wall. And the shoring wall extended like, say, 10 to 12 meters, somewhere here. This is the soil column. You have 11 meters of sand and very weak sand here, very, very loose sand at the bottom part. Then very weak rocks of sandstone. The shoring was extended up to within the rock part, and the nearby piles, they were very close to the shoring, and they don't have enough length below the shoring. Shoring wall causes less frictional resistance for the pile at the side of the shoring wall, because there's no much continuity of the soil that can resist the applied loads. So if you depend only on end bearing resistance, you need longer piles and larger diameter piles. Usually we depend on the skin friction a lot. Anyway, these piles were supposed to have enough length, but two problems occurred. The first problem was the piles that have really failed, they were near the shoring wall. And second, that the difference in elevation estimated by the soil report for the rock layer was different in 2 to 3 meters than the existing rock layer elevation. So the socket within the rock layer was shorter than required. And another problem occurred later when analyzing the structure and the superstructure. They found out that the structural analysis showed that the loads on the piles may be more than the original design loads. And what happened is cracks over the columns in the basement, and the cracks continued to a couple of stories from the superstructure, and cracks everywhere in the basement slab and some parts of the walls as well. But mainly the dangerous cracks were in the basement columns, which support the whole structure, while the inner columns were not were in a better situation, in fact. You need to leave enough space for concrete. You can't install such a cage. This is ridiculous. There's no place for the concrete to flow between the reinforcement bars. So you need to either increase the diameter of the pile, or to find or to add more piles, or to find another way to decrease the reinforcement. You need enough, at least 4 to 5 times the bar diameter, and minimum 100 millimeter between the pile reinforcement bars, so that you ensure the consistency of the flow of concrete. We have different types of problems in piles. So we have contaminated pile heads, that you expose the pile head and you find it contaminated, not sound concrete. And of course that is found easily by a core test, or by sometimes even with your hand you can remove the pieces of the gravels and cement from the top of the pile. You have another type of defects, that is reinforcement shift. It may shift laterally or get damaged, and it may shift vertically, and the vertical shift may be up or down. So the reinforcement may fall down, or the reinforcement may stay above the cut-off level. Top of concreting may be lower than the required level, and sometimes more than the required level. That's cost. Piles may be shifted in location. Wrong coordinated installation, or because of tilting of the machine. Piles may be inclined more than accepted, so there's a special limit for the inclination of the pile in the design. The tolerance is usually 1 to 13, or sorry, 1 to 75, say 13%. 1.3%, sorry. Piles sometimes fail in integrity, so there are weak zones in the pile shaft or voids or gaps. Integrity is tested by either a low strain integrity test or by sonic core logging test. The best way to test the pile for its integrity is the dynamic test itself, dynamic load test. Pile may fail in material requirements, like the concrete strength or durability of the concrete tests. You test the durability and you find out of the limits, or the concrete strength, you find it less than the required design concrete strength. Piles also may fail in design requirements. They are unable to match acceptance criteria in load tests. Sometimes SI reports do not match piling bore logs. This is very important, by the way. That's why I say always you need to have a trial boring and check your SI report, the soil investigation report, with the outcome of the boring. With every level, you need to check that the soil report was correct, so that your design will be adequate. Piles may fail in caliper logging, so you have larger diameter, smaller diameter. You may have problems later on in the cover for durability. I have checked couple of, not couple, in fact, many projects, and I got these percentages. So I have the total number of defected piles. It's around between 6 to 7%, and these are the percentages of different types of defects. You can see contaminated heads is the next to the total number. So most of the defects in the piles, these are for foundation piles, by the way. This graph is for foundation piles. It's not for shoring. So contaminated heads usually are 3% of the projects. We're talking here about huge projects. We're talking about hundreds and thousands of piles, not a project having 10 to 12 piles. You can easily control the production of 10 to 20 piles for a small project. This is an interesting problem also we faced in one of our projects. The soil report indicated a couple of boreholes around the plot. This is the plot that we are constructing a multi-story hotel on it. And the plot was just near the water body. It's part of the Gulf in the Middle East, in UAE. And the hotel shape is, the podium shape is exactly the plot boundaries shape. But the soil report have shown that there are different levels for the rock layers and different rock layers at different locations. Of course, the estimation of the location of the exact coordinates and existence of these rock layers cannot be estimated by only the boreholes. And if you construct your pile foundation on such foundation soil or foundation rock, you will get huge differential settlements. Because you can't say, let's use 30 meters piles for this load, considering the lower part of the rock layers. While the on this side, for example, the 30 meters will be almost fully in rock. So these piles will not settle, while these piles will have some shortening. So what happened is we needed to decide a method to construct the rock layers, how they look like and where are they located. So what I suggested, and it was done, I suggested to use 200 points of CPT test. I don't need the values of cone resistance or frictional ratio. I just need that the cone resistance reaches really to limits of refusal of the rock. And that's how we knew where are these rock layers everywhere. So this is the top of the ground, let's say the ground surface, and these are the rock layers. And because we know what type of rock layers we have from the boreholes, we could estimate the shape and the location of the rock layers. After that, we could design the piles with different lengths, even for the same loads, based on their locations. Everything went fine. This is another site. Of course, if I introduce all the problems that I have seen or collected in my life from my projects or other people's projects, it will take too long to show everything. I have thousands of photos and hundreds of projects with different cases, but I'm trying to present some interesting ones. In fact, in this project, the shoring wall was from +3 ground surface to -18 at the tip of the shoring wall. They were secant piles, and this is the excavation level, and we were having dewatering wells to -19, and we started dewatering, and everything looks fine, but it's one of my my habits to observe the water behind the wall during shoring. So always I install piezometers around the wall. In this project specifically, we installed piezometers behind the wall in a couple of locations, not too many. I think 2 or 3 piezometers in one side. This project is very near, is very close to the sea. So it's around 100 meters from the sea. The shoring wall is about 100 meters away from the sea. The soil report has indicated large coefficient of permeability for these rock layers. We did a pumping test before start, and the pumping test was also indicating good permeability. But unfortunately, the pumping test was not very deep. It was in the top parts, and later on we found out that this calcarnite layer, it's a massive sandstone and it works impervious. it does not allow water to flow. So what we had, the groundwater behind the wall did not go down really. The drawdown was only 0.5 meters or something like that. Then I started to monitor the deflection as well, of course. And I'm testing everything around me. What's happening? It's a huge project, and we need to be sure that everything is going fine. Some areas were 2 rows of anchors, and some parts were 3 rows of anchors. And the anchors were not very long because of limitations from the authority for the extension of the anchors. So I'm in the critical situation, not really very happy. So when we are going down with the excavation and the water is not going down, I started doubting everything. With the extensive, not extensive really, with the ultra deflection that I had at the top near the first row of anchors, I understood immediately that the water pressure is working and it is not as designed to get lowered by the dewatering system. So we opened holes in the shoring wall to decrease the pore water pressure. And with these holes, the deflections stopped immediately and even went back. The hole went back. The water flowing, but we need to collect this water in some way. This is not possible to be collected if you don't use the dewatering system. We did a simple pipe, PVC pipe, with a deep hole inside, like 1 to 1.5 meters, and some were even 2 meters, to collect the water. So releasing the pore water pressure at the top part stopped the deflection. And these PVC pipes were connected, and the water was guided into the deep wells. So we have a pipe and a trench covered with gravel, and goes into the wells. This way we control the pore water pressure behind the wall. But this project did not stop problems at this level. Have a look to this one. This is the site after excavation, and they are starting to install the piles, the foundation piles. And unfortunately, water started flowing out of the foundation piles. See, this one is drilling here. There's no problem, but these two are fully covered with water. The water is flowing out of these 2 piles. What happened, in fact, is this. So this layer is getting dewatered, and the dewatering, instead of having a drawdown curve like this one to lower the original groundwater table, the dewatering could not take the water from the above layers. So it was only horizontal flow from the sea directly to the dewatering wells. Dewatering wells were not deep enough into the mudstone layers, because mudstone should be impervious. But so, and you cannot make very, very deep wells, in fact. The deep wells were increased from 10, 12 deep wells into 28 deep wells in this project. Anyway, we expected that the mudstone is impervious, but what happened, it looks like that the gypsum layers embedded within the mudstone were not massive or were not crystalline gypsum. They were permeable enough to let, not in every place, but in some of the locations, to let the water flow into the holes drilled by the machines for installation of piles. So water was flowing from below the deep well. Deep wells could not control that water because it's coming from the from a deeper part. So some of the piles were really having this problem, and they were solved in pouring fast concrete, and we extended some of the lengths of the casings to control the water as much as possible. Because in rock, you don't need long casing. You need only 1 or 2 meters above the top part, I mean. So in this case, you need to extend your casing. This is a closer look. With this slide and this small video, I end my presentation. I hope it was nice and interesting for you all. Thank you for all the attendees, and thank you for your kind listening. Sen?
Okay. Okay, thank you for Dr. Mufty give us a very interesting and practical presentation. And then we received some question, but due to the time limit, first I'm going to choose probably 2 or 3 questions. And the first one, very simple. And the attendant just asked, because of the interest in the topic, where your presentation slides be distributed to attendees. So, you can answer this with the other question. And the second question is raised by the Jason and asking about segregation of the concrete in pile can also happen due to free fall of the concrete into deep piles. What is your experience with the limit of the depth allowable for concrete for free wall versus when concrete placement should be switched to trimmy pour? So I think you probably can answer this question first, and also the first question.
What was the first question again?
First question, just can you attenders just ask, can you share this your presentation slides to the attendees? And the second question.
Yeah, this is up to CGS. How does it work in this case? I believe we can do some PDF format of it. I don't know. It's up to you.
Okay. Okay. Sure. Yeah. After you send us a PDF file, we may upload this into the website for the attendees who are interested to download. Okay. Yeah. And the second question is regarding the segregation of the concrete. So yeah, what you recommend?
Yeah, segregation. I said it may happen due to washing out the fines and the cement due to dewatering or flowing water or flowing cement from one pile to another hole. And also I said it's because of low slump. So if you have low slump, you may have a honeycomb void structure within the concrete. So if you have a free fall of concrete, you should not really go to, first of all, we do not use a free fall of concrete into slurry or into water. It should be dry hole. So if it is a dry hole and you have enough slump, you will not have this problem. But if you don't have a slump, if you have a slump less than 150, for example, 150 millimeters, you may have this problem. So increase your slump and you will be okay. If you have water, or if you have a slurry, or you have a polymer within the drilling, within the hole as a drilling fluid, you need to use trimming. You can't have a free fall. So segregation using the trimming occurs because of these two things. Either your slump is very low, so the concrete will not get compacted, and the second and the major cause in many of the sites that have dewatering or sequencing of piling is not adequate.
Okay.
I believe I
So,
answered.
yeah, thank you. And do you have a recommended depth between the free fall and the trimming bore?
No, I said trimming is a must. If you have fluid in the hole, trimming is a must.
Yeah.
If you have a dry hole, you can use the free fall.
Okay. Okay.
Just have enough slump.
Okay. Thank you. And the following question is raised by Ahmed. Given that your experience is both in hot and the humid and the cold countries, what is the main difference and the difficulty associated with construction of pile and the concrete? I think the question is regarding the difference, the difficulty between the weather, different weather conditions.
The question is answering itself. The temperature is very important. If you have huge amounts of concrete poured in the same day into one hole, especially the piles for the huge towers are of large diameters, like 1.2 to 1.5 and sometimes to 1.8 meters diameter piles with 50 or 40 meters length, you're pouring this concrete in one shot, in one day, in a continuous process. You will have thermal effects on the concrete very clearly. So you need to have your temperatures controlled while you are bringing the concrete into the site. All the mixers coming to the site, they have very, very controlled temperature, and the temperature is taking many times before you start pouring. This is very important. Also, we have retarders used in concrete so that you can control the setting time and the hardening, the shrinkage effects on the hardening. Yep.
Okay. Okay. Thank you. Just according to your probably first or second presentation slide, you showed some seepage passing through the shoring piles, shoring wall. Yes, and you mentioned that dewatering, of course, is important for the remedial work. You mentioned that the additional dewatering may be considered, of course, but the question for the timing consideration, do you also consider other emergent treatment, for example, have the grouting or whatever, just because of the timing, to stop or reduce this amount of the seepage?
Well, it depends. If your wall, if your pile wall, your shoring pile wall is a second piles, already second piles, it's a watertight system. So if there is a leakage somewhere, you can grout, you can stop that leakage. But if your wall is contiguous piles, already there are gaps between the piles. And the material behind the gap or behind the wall is made of sand and made of overlaying rock layers. Grouting will be impossible, maybe. It's not easy because you grout and it will flow with the water between the piles through the gaps. Dewatering system was already installed in these projects, and it was working, but it did not need to work in a capacity compared to the flowing water between the contiguous piles. So you need to do these French drains and collect the water into deeper wells and increase your capacity of your discharge capacity of these pumping pumps, I mean.
Okay, thank you. And also, according to the one of the slide you present in the comment about the shorter reference beam for the parallel test, and according to the photo, it can be observed the distance of the reference beam to the edge of the test pile may not also sufficient. So I think this is maybe also one of the question, the issue to create the untrustable, unacceptable result of the pile test.
The distance between the reference beam and the pile itself or the pile cap is not important because the reference beam is already above the ground. But the length of the reference beam is important. The supports that the reference beam is seated at, or the reference beam supported with, these support points should be away from the pile. And usually it's asked to be more than 3 diameters in each direction.
Yes, okay, thank you. I think that because of the time limit, I think we may need to stop here. And thank you for your presentation again. And also thanks for all the attendance for this webinar. And we may see you for, on April 22nd for the next event. Thank you, and good afternoon. Thank you very much. See you.
Thank
Bye.
you. Thanks, thank you.